Okay, so we've got some questions about last week's work, which if one person is struggling with, that probably means that many people are. So we're going to go through the questions together. Question number one, is the dot for free radical supposed to go before or after the molecule's formula? Well, the short answer is it doesn't matter. Let's say you have a methyl free radical. You could put the dot on the right hand side or the left hand side, it doesn't matter. You'll more frequently see it on the right hand side. So that I think is question one answered. Question two is about question one worksheet 4, which is here. This is question one worksheet 4, and it's about ethanol. All right, so it's about the molecular ion of ethanol, and we're going to fragment that molecular ion and into different fragments, and we have to identify them. Okay, so the first thing to do is to draw out our molecular ion of ethanol. All right, so here's our ethanol molecule. So that is ethanol, and it's a molecular ion, all right, which means that it's had an electron knocked off it by the bombarding electron, but we don't know where that electron has come from. All right, so it could be anywhere on the molecule. All right, so we just put square brackets around it and a plus sign. Normally in exam paper you'll just see it written in this format, where you just got the structural formula and a plus. But because I've drawn it as displayed formula, I've drawn the square brackets as well. Okay, so that ion is possibly fragmented. Okay, so let's say the fragmentation occurs here, where I've drawn that black squiggly line. Then in that case you could get a couple of possibilities. You could get a methyl free radical. Right, so let's draw that here. So you could have the CH3, and if it was homolytic bond fission like this, and the electron had not been lost from that part of the molecule, you would get a methyl free radical, but that wouldn't show up in the mass spectrometer, right? So that wouldn't create a peak. You'd only create a peak if you get this ion, right? So you get methyl positive ion, all right, like so, and again draw it in square brackets, all right, and it's been fragmented, and it's still got a charge, so it makes its way through the mass spectrometer to the detector, and so that's how you would get something that has a mass peak of 15. See, we've got one positive charge, we've got a mass of 15, so that corresponds to this bit of data, and what you would write in here is just CH3+. Okay, so let me just change colour to green. So if I use the original molecular ion, all right, but if you ignore the black bit, and instead it breaks here, then you could apply the same principle, and you could get an ethyl free radical, or you could get an ethyl positive ion. All right, and the ethyl positive ion would be have a mass charge ratio of 29. So what you would write in here would be CH3 CH2+. Okay, so that fills in those two boxes. I think these two boxes here are simpler now, at least, where you just take the mass of the ion and by counting up, like for example here we've got 12 plus 2 is 14, plus 16 is 30, plus 1 is 31, right? So you'd write in 31 there, and the same for this one down here. So I think that's part A done. In terms of the equations in part B, let's do the equation for A, because then we can use this here. Okay, so we started off with the molecular ion of ethanol. Yeah, so that's what we need to write here. Let me do it in blue. Right, so you started off with structural formula of ethanol, CH3, CH2OH, right, but it's a molecular ion, so we're going to put our plus charge there. And that's fragmented here where we had that black line that I've just overdrawn there. And we wanted it to create a methyl positive ion, all right, so that's our CH3 plus. So what remains is just the balance of the molecule, all right, so the balance of the molecule is the CH2OH. All right, it has to be a free radical, all right, and we would, because the bond has broken next to the carbon, we would draw our spare electron on that carbon there on the left hand side. So that would be the answer to part A, and you follow the same process for the others. So hopefully that's answered your second question. Right, so going on to the third question, let's make a little bit of space here. So the third question here, don't understand what the n+1 peak is. Right, the n+1 peak. So first of all, you've got the molecular ion peak. So if we had, let's draw a very rough spectrum. So you get various peaks everywhere, and then you've got the last big peak right here is going to be the heaviest molecular ion that you can get. And that's when you've only lost an electron. All right, so this corresponds to the MR of the molecule, because you can't add to the molecule. You can only the minimum you can take off the molecule is 1 electron, so the mass is the same. So that's the molecular ion peak, right? But let's draw out ethanol again, and excuse me while I just draw it all out. All right, so a most common ethanol molecule would be this one would be a carbon-12 isotope. This one would be a carbon-12 isotope. This would be hydrogen-1 isotope, hydrogen-1 isotope, hydrogen-1 isotope, hydrogen-1 isotope. Yeah, oxygen would be a oxygen-16 isotope, and hydrogen would be a hydrogen-1 isotope. So the most common molecular ion, when you knock an electron off this molecule, the most common one would be the normal MR of that molecule, which is 1546. Okay, so let's change to purple. However, 1% of naturally occurring carbon, right, so 1% of carbon is actually carbon-13 isotope, right? And 1% is quite a reasonable percentage, right? So there is a chance that one of these two carbon atoms is actually a carbon-13, right? So let's cross out that 12 and write a 13 there. And now the MR of this molecule, all right, is the same plus 1, right, is 47. All right. Now the chances of both carbons being carbon-13 are very small, because it'd be 0.01 times 0.01, so undetectable at the resolution of normal mass spectrometers. So that is why we get an n+1 peak, right? Because you see 47 is plus 1 compared to the molecular ion peak. Now that doesn't happen with oxygen or hydrogen, because the isotope, take hydrogen for example, you could feasibly imagine a deuterium atom replacing one of these hydrogens, right? But deuterium is much less common than carbon-13, and it's about 1 in 1,000 molecules, right? So that also would do it. So there would be the odd molecular ion that would have a deuterium, right? But it would be indistinguishable on the mass spectrometer. So that's why, right, the fact that you've got a reasonable proportion of carbon-13 atoms out there where one of the carbons is a carbon 13, makes the N+1 peak. So hopefully that's explained question